Okay, question number 3, and it says explain why the potentials have a negative sign. So you have to think about what potential is. It's the work done moving from infinity to a point in the field. So it's the work done moving a positive charge of 1 coulomb from infinity to a point in the field. If you're working against a repulsive force, if the charge that's creating the field is positive, then the force is repulsive because it's a field radiating outwards, and so you have to do work to overcome that repulsion. However, if the charge is negative, the charge that's creating the field is negative, then the force is attractive, so you're not actually doing work overcoming the fields, so the work done would be negative. It's worth, for point 2, it says draw a copy of the diagram, draw on a copy of the diagram 3 electric field lines. So there they are. You need to make sure that they are even angle between them, and have arrows heading towards the charge. It's worth quickly pointing out at this point, obviously, the position of these equipotentials. Now, if the potential due to a field is 1 over 4 pi E naught times by Q over R, then if this is the position, if this distance here from here to here for the minus 80 volts, let's just say we call that R, if we doubled it to this distance here to 40, then of course we should get the potential being half, as long as this charge stays the same. So this distance from here to here, if that's R, then to 40 should be 2R. Now what you should then find, if we said, if this is 2R, doubling it to 4R should halve the potential then, and then doubling that again. So each time you go out along here, this is double that, this is double that, and this is double that for us to go down, halving each time. Okay, and it's probably, you can see it probably better if you measure it in the book. You'll see it better in the book. Anyway, that's a bit of an aside. Anyway, B asks us to use data from diagram to show that the charge Q is about minus 4.5 times 10 to the minus 11 coulombs. So when you get on your diagram, you get the actual book here and measure the distance from charge Q to the minus 10 volt line. It comes out to about 38 millimeters. So we plug that into our potential equation. Potential was minus 10 when R is 38 millimeters. This slot here is equal to 9 times 10 to the 9, and so Q comes out to minus 4.23 times 10 to the minus 11, that's not very well drawn, times 10 to the minus 11 coulombs. Okay. B part 2 says calculate the electric field strength at B, and B is on the minus 10 potential line. So the field strength, of course, is the charge divided by R squared times this constant. I just used the value that I got from there, 4.23, but you could use minus 4.5, whatever. It doesn't change it massively. And that comes out at 263 volts per meter or newtons per coulomb, whichever you prefer. It should be to 2 sig figs really, so it should be 260. That's the proper answer. Okay, question 3C, it says calculate the energy in joules transferred when an electron moves from A, which is on the minus 40 volt line, to B, which is on the minus 10 volt line. Now, obviously you'll know for potential difference is the work done per coulomb, joules per coulomb, basically GCSE. Therefore, potential difference times by charge is the work done, and therefore the change in potential is the potential difference times by the charge is the work done. So these are potential lines, and if we go from one to the other, that's a potential difference. So we're going to go from minus 40 to 10, so we want the final minus the initial, that's minus 10 minus 40 times by the charge, which is minus 1.6. Lots of minuses in here, and it comes out to minus 4.8 times 10 to the minus 18 joules. Now that sort of indicates, that tells us the answer to the second part of this question, 3C part 2. Calculate the energy in joules transferred when an electron moves from A to B, and state and explain why the kinetic energy of the electron increases. So because it's negative, it means that it's lost potential energy. Okay, if it's lost potential energy, it must have gained potential energy. Now the second part of that question, C part 2, says explain also how the de Broglie wavelength of the electron changes as it moves from A to B. Well, the de Broglie wavelength is given by the Planck's constant divided by the momentum. So essentially, if it's increased its kinetic energy, it's also therefore increased its its momentum. So if it's increased momentum, because that's on the bottom, will have decreased the value for the de Broglie wavelength will have decreased. Okie dokie, that is question 3.